Hello everyone, welcome to our presentation about Neon Noir demo, ray tracing on mobile. My name is Morteza Mostajab. I'm a rendering engineer at Crytek. Our talk is split into two parts. I'm going to briefly discuss rendering pipeline used in this demo, and Vladimir will cover software ray tracing on mobile in details. Before talking about anything, here is our demo. So Neon Noir was a tech demo first shown in GDC 2019. It announced our software-based ray tracing technology and was benefiting from latest features of our engine. In this short sequence, we were seeing part of a city lit with more than 130 lights and 18 environment probes. The scene was using about 4 gigabytes of texture. The key part of demo was to showcase real-time physically correct reflection of static and dynamic objects in CRYENGINE. Since the technology was built by commonly available modern graphic API constructs like compute shaders, we decided to simplify the lighting setup and try the same scene on a flagship mobile device. Our first experiments with CRYENGINE's Forward Plus mobile pipeline was very promising, but there's still a few other passes that needed gbuffer information as input were missing. Therefore, we decided to switch to deferred shading. One of the biggest challenges for deferred rendering on mobile chipsets is their low memory bandwidth compared to PC and consoles. To tackle this, we have a compressed gbuffer representation called micro gbuffer. In this method, we store geometry data at lower rate than actual render target resolution and reconstruct it during sampling it. We use a checkerboard pattern for storing the micro gbuffer with even pixels containing albedo luma, albedo blue difference, smoothness, and reflectance as luminance value. For odd pixels, we store albedo luma, red difference, and X and Y components of normal vector. For a full HD game running at 30 FPS, this method consumes 1.9 gigabits per second of memory bandwidth, which is 66% less than CRYENGINE gbuffer on PC and consoles. Here we zoomed on micro gbuffer texture to show its encoding representation. The checkerboard pattern is clearly visible. An example of different gbuffer components reconstructed is shown below. Since we use an edge-directed reconstruction based on albedo's luma component, the method may leave reconstruction errors where other geometric components change at higher frequency than albedo. In the bottom right image, the window frame has almost a constant albedo color as the edge of, and so the edge of it is not detected. Therefore, micro G-buffer reconstruction has produced the checkerboard artifact. Here we see some statistics about scene rendering in Neon Noir and comparison between G-buffer and micro G-buffer performance on mobile. In average, in this demo, we have 1500 draw calls which render 160,000 triangles per frame. These numbers go up to 6,000 draw calls and 400,000 triangles per frame in some views. Frame time is 38 milliseconds, which around 10 milliseconds of it is scene rendering and shading. As the table shows, by using micro G-buffer method, cost of deferred shading is reduced by 35%. Here we see the full overview of rendering pipeline used in this demo. We tried to utilize Vulkan's subpass functionality as best as we can to reduce tile memory resolves and bandwidth consumption. Render passes with its subpasses are grouped together and shown in this picture. In the pipeline, we first render the scene and fill G-buffer. Since linearized depth is used by multiple different passes, we'll linearize it and store it as a separate texture next. Then we apply raindrops effects to G-buffer output and then downsample depth buffer. The downsample depth is being used by Raytracing and volumetric fog stages. Both Raytracing and volumetric fog stages run as compute shaders in our pipeline. We have observed noticeable performance benefit using compute shaders for ray tracing. The mobile shading pass applies lighting to G-buffer and composites ray tracing output over the lit G-buffer. After that, forward passes are running, and then fog stage applies the global fog and volumetric fog output on top of final image. Then falling raindrops is added to image. At this point, we stochastically randomly sample luminance of resulting image and download them on CPU to estimate the brightness of final image for adjusting exposure in Tone Mapper later. We have presented the details of this method in a poster in this year's High Performance Graphic Conference. Then we apply depth of field and bloom effect on top and tone map the image. To reduce aliasing artifacts, we apply temporal anti-aliasing method. Here we see average execution time of the frame broken into different stage cost. So scene rendering and shading takes about 25% of the frame. Ray tracing cost is about 35% of the frame, and depth of field is 15% of the whole frame. These are the three major costs for a frame. Here in this slide, some of the important optimizations we used in the demo are mentioned. Since using a smaller HDR target format causes less bandwidth usage, we switched from a 16-bit floating point per channel to 10-bit integer per channel. That reduces the required bandwidth for HDR target to half. Previously, we were storing required light information for shading passes in a storage buffer. And when we switched to uniform buffer, the shading cost of actual scene and ray tracing output is reduced by 4 to 6 milliseconds. We also try to use relaxed precision whenever it is possible to reduce pressure on ALUs. We tried to use proper render path setup with as much as subpaths possible with most optimal load and store operations to make sure we only store and load the data required for each render path. Also, we tried to scale down effects on mobile. For example, we reduced the number of far near layer iterations of depth of field to drop 2 milliseconds of the frame cost. We also reduced volumetric fork resolution by 40%, and that also dropped another 2.4 millisecond cost. Thank you for your time. Vladimir will continue the presentation.
So hi guys, my name is Vladimir Kajalin. I am principal rendering programmer at Crytek. So during many years I worked on most of the Crytek's projects and many subsystems of the CRYENGINE. I will present now the solution we used in Neon Noir mobile demo for ray traced reflections in real time. I have to explain that ray tracing work we're presenting here is not really a final, polished solution, but more a research in progress with multiple questions not finalized. So a few highlights of the demo. We use ray traced reflections for most of the smooth and glossy surfaces. For example, glass windows, water puddles, and some other surfaces, including drone body. Most of the objects are visible in reflections: buildings, streets, all emissive objects like neon signs and streetlights. Objects in reflections are properly lit by most of the scene lights and environment probes, which allows us also to simulate reflections in reflections. Shadows and fog also applied as well. We stream ray traced data from disk on the fly, and it means we are not limited by the size of the scene. And for example, much bigger part of the city will work with same performance. Ray length is high enough to handle most of the reflections with ray tracing, and also to make sure that transition into environment probe reflections is not too obvious. Few words about internal structure. Okay, on CPU side, for static world, we incrementally stream BLAS data from disk and upload it to GPU. For dynamic object, and we have only one in demo, we rebuild BLAS every frame. We also stream in material textures like albedo, normal maps used in ray tracing and also uploaded to GPU. Every frame we regenerate single global TLAS and relink all the prepared BLASs into it. On the GPU side, for every frame we perform several passes: ray generation and tracing pass, hit point shading pass, and basic denoise pass. So how do we pre-process static geometry? The world is split into 32 meter segments, you can see on the image. For each segment, we collect the static triangles and generate BVH for it. During BVH subdivision, we consider the surface area of the node bounding box and the number of triangles in the nodes in order to estimate the tracing cost and find the most efficient split planes. Normally, we have maximum 4 triangles in BVH leaf node. We limit the tree depths by 12, mainly because we have hard-coded stack size in the tracing shader, so we have to define some maximum depths of the tree. For each segment, we also collect material information and prepare the material textures. We limit the texture size by 256 by 256. The textures are stored in the one big 3D texture, and this allows the tracing shader to access all of them just by ID. Every frame processing on CPU. For every frame, we relink all active static BLAS segments, we have about 8 of them, into one global top-level BVH tree. This tree has only few levels and it is very small in memory, so it can be quickly generated in real time and then uploaded to GPU. No triangle data upload is necessary at this stage. For movable objects, for the drone, we use a bit brute force approach. Every frame we collect the triangles and generate from scratch one global BVH, constantly containing only dynamic meshes. The tree depth is limited to about 6, so it can be generated faster. Also, we use lower LOD when object is far away. So here are 3 rendering stages we have on GPU. And also here are examples. Here are examples of the content in the render targets. Tracing pass takes as input gbuffer data like scene depth, normals, smoothness, BVH and triangle data, and also material information and material textures. If smoothness is high enough, the reflected ray is calculated and ray-scene intersection is performed. Once we found closest intersection, the material info at hit point is sampled. The output of the tracing pass is the information about ray intersection point and material we hit. Shading pass takes all this info and also takes information about scene lighting and performs the shading of hit point. The output is final shaded RGB value and also a ray direction. The output of the shading pass may already look good enough to be used as a mirror reflection, but usually it suffers from aliasing, especially if we perform tracing at resolution much lower than screen resolution. Because of that, as final step, we perform temporal stabilization and denoise pass. Some more details about tracing and shading passes. Since we want to find closest hit point, it would be more efficient to traverse the three nodes in sorted front to back order. In order to achieve this, every GmbH node keeps the ID of the split plane axis used to subdivide this node. During traversal, this ID is used to quickly find out what child has to be visited first, and as a result we get massive reduction in the number of nodes traversed. In GmbH traversal shader, we use stack of 12 node indices. We plan to investigate stackless traversal in the future, as it could help us with GPU occupancy and better performance. Shading pass is as important as tracing pass. Without proper shading, the reflections may easily look inconsistent and not fitting the scene. Because of that, shading pass must support all the lighting solutions we used in the main view. In this demo, we supported sun, point lights, projectors, environment probes, and global fog. Some more advanced techniques like clip volumes were simply not used in this demo. And we use 3D grid as acceleration structure for fast search for the lights affecting the ray hit point. Denoising. In this demo is mainly performing the temporal filtering for less aliasing in final image. Common reprojection approach is to use difference between camera matrices of current and previous frames and find screen space location, X, Y, and depth of the pixel in the last frame. This is common technique working fine, for example, for temporal AA or for denoising of AO. But in case of mirror-like reflections, we have to deal not with the surface itself, but with the surface visible in the reflection. In order to properly reproject the reflected surface, instead of scene depth, we take total visual depth from the camera to the object reflected in the mirror, which can be calculated as sum of the surface depth and the distance from the ray origin to the reflected object. This is basically working same as if we assume that reflection of the object in the mirror is an actual object, and in this case we can just use total distance to the object in order to reproject it into last frame. So quick overview of the data structures. Normally we try to compact the data for better cache coherency. For example, we pack vertex position and other vertex attributes into a single 32-bit float value. In order to compensate precision loss, we store vertex position in the space of the GmbH node bounding box. We keep the data not only compact but also adjacent in memory to avoid scattered reads and trashing the memory cache. We store all three vertices of triangle together in one data chunk, and also we store triangles in memory right after the GmbH node descriptor. Obviously, one of the ways to speed up ray tracing is to reduce the number of rays. We shot rays only for surfaces where it really makes sense. We test the smoothness and reflectance. Ray tracing is really important for sharp mirror-like reflections, but in case of rough materials, old good cube maps still works just great. Next, we trace at low resolution. We ended up tracing at 30% lower resolution comparing to the screen resolution. This way we get 0.5 rays per pixel. Next, we tried interlaced tracing. Same as in old analog television, we compute odd lines on odd frames and even lines on even frames. This reduces number of rays twice, but brings interlacing artifacts. In order to compensate it, we perform deinterlacing steps during our denoise stage. During our temporal reprojection and blending, we give more priority to the most up-to-date data. In other words, when new data is missing, we reproject old data into new camera view. On those screenshots, camera is panning quickly, and on top image, you may see interlacing artifacts are very visible. On bottom image, bottom image is deinterlaced using this technique. Another obvious way to speed up the rendering is to optimize the content. We automatically include only relatively big and most visible objects into BVH. We also give artists the tools allowing to exclude individual objects or entire sections of the level from the BVH. Next, we use simplified version of the geometry for ray tracing. It could be regular LODs or special meshes made just for ray tracing. Reducing the resolution of material textures also helps with performance. On top of that, we don't use alpha test. Ray tracing and alpha test is usually a slow combination, so we get about 25% faster tracing without it. Good profiling tools for content creators are very important, especially on mobile platforms. Because of that, we provided several debug views allowing the artist to quickly find performance-heavy assets and possibly optimize it. So first we have basic visualization of BVH tree by showing bounding boxes of BVH nodes. Then we have performance heat vision mode, where pixels producing too much shader work are displayed in red. Also we made primary race debug view, where tracing is used instead of main view rasterization, which is really great in combination with performance heat vision. This is basically it. Thank you very much for your attention, and please feel free to ask any questions.